Hi, my name is Mike Splash. I'm Senior Hydrogeologist at the Dragon Corporation. We're an environmental consulting firm with offices in the United States and Canada. I'm hosting this series of webinars that provides you with 10 tools that will help to solve your groundwater contamination problems. My colleague, Matt Schroeder, is going to talk today about high-resolution site investigation techniques. Take it away, Matt.
Hi, I'm Matt Schroeder, and I'm an engineer with Dragon. Today I'm going to discuss some of the tools that we've recently been using to improve the information we're able to collect during our soil and groundwater investigations. In traditional investigations, we collect a few data points in boreholes spaced hundreds of feet apart. When groundwater sampling, samples were often collected from monitoring wells with maybe 5 or 10 foot screens. Once we had this limited data set, we typically interpolate between the data points to build our site conceptual model. Sampling methods and interpolation tended to smooth out the sharp transitions in the data that often exist in heterogeneous geologic environments. More recently, we use tools that provide hundreds to thousands of data points in each borehole. Because these tools are most often used with direct push or Geoprobe drilling equipment, more boreholes can be completed in a given time and cost. We're able to obtain much more dense data set through this high resolution site investigation. So today I'm going to discuss 3 techniques that we've used for high resolution site investigation. I'll give some examples of how we've used them on projects to save both time and money. So the first one I'm going to discuss is multi-level groundwater monitoring systems. Typically we might have, as I mentioned, a 5 or 10 foot screen in a monitoring well, and usually just the one monitoring point at each location. The advantage of the multi-level monitoring wells is that you get pieces of information from multiple places within a well or within a single boring rather than just a single data point. It's especially useful where drilling is expensive, say if they're deep wells or in bedrock. One thing you have to keep in mind, though, is that for compliance monitoring, these might not get approved, but they're particularly useful when you're trying to do delineation and trying to get the vertical distribution of contaminants, or even possibly for checking remediation. You can get a much greater density of data down gradient of where you have done a remediation to try and see what the effect is. So on the left here, we have a conceptual site model of a site where they're using the continuous multi-channel tubing to monitor between the source and a receptor. And you can see that they've installed lines of these boreholes where they have multiple screens where they're able to gather data to be able to get a 3-dimensional picture of where the plume is. On the right, you can see the actual physical tubing that gets installed. You can note that there's 3 channels in that tubing. You can have up to 7 different channels, so 7 different data points within a single vertical borehole with this technology. A couple more pictures of how this is implemented. So it comes in a big roll, and you can see on the left-hand picture them rolling the tubing out and cutting it to the right length. And then on the right-hand picture, they're installing some hardware in the 3 channels. And then here you can see a picture of the installation of a screen, and you can see it's right in line of the tubing, and you can have multiple screens, obviously within a single set of tubing, to be able to take samples from different depths within the borehole. And here you can see them actually installing the tubing within a borehole. They typically have a centralizer to keep the tubing in the center of the borehole, and as it's being installed, you have to be careful to make sure you get an effective seal between the screens, so that there'll be sand put around the screens to allow for the water to enter the screens. But between the screens, we don't want vertical communication between the areas. So we put a bentonite seal or something that's impermeable between the screens within the borehole to make sure they're isolated from each other. So something similar, but maybe a little bit different, is a packer system called the West Bay system. And what this is used for is if you've got a well that has a long screen, or maybe an open bedrock borehole, that you want to be able to get vertical distribution of contaminants and be able to see what might be present in a small section of that borehole or screen. And so this packer system can be lowered down the borehole, and you can see on the left-hand part of this, the blue areas are a bladder that you fill up with air, and it seals tight to the side of the borehole or to the side of the casing, and that isolates the spot between the packers, and you can collect a sample from the ports that are installed within the system there. And the advantage of this is, as I mentioned, you're able to get a better vertical distribution, but you can also reuse it, because by deflating the bladders, you can pull the system back out of the borehole and potentially use it in the same location again or another location. So some other things that have been gaining popularity lately are tools that work along with the Geoprobe system. And one that we've been using quite a bit is the hydraulic profiling tool by Geoprobe. And what that gives you is a log of the permeability as you advance the Geoprobe equipment down a borehole. So as the probe is advanced, you can see in the picture of the tool here, there's some little ports on the side of the tool, and a small amount of water is injected from the tool, and you measure the pressure that injection of water generates. And from these pressure measurements, you can get a profile of the hydraulic conductivity, because in finer grained soil with less hydraulic conductivity, it takes more pressure to inject that water. The high conductivity zones will show a lower pressure. And these are often what we're trying to find, because that's where the mass flux can be greatest, and that's where you need to identify where the contaminants are for remediation. So this is an example of a hydraulic profiling tool log, an HPT log, that we did prior to conducting an aquifer test at a project of ours in Salina, Kansas. This is an area with a very mixed geology of sand and clay, and so we're never sure exactly where we're going to find the permeable zones, and we wanted to make sure that we had a good permeable zone to be able to conduct an aquifer test. So we advanced the HPT probe, and you can see the log of the pressure in the middle here. And some things that you can tell here is where there's high pressure, so where the line is out to the right, that's where we have clayey material. And then you can see that where it drops off to low pressures, that's where we have sandy material. The right-hand side is a interpretation of that, showing where the sand is shaded in red. Another thing that's interesting about this is you can pick off the water table, because as they are advancing the probe, periodically they'll stop and get the kind of ambient pressure. So basically the pressure that it drops back to when they're not injecting any water. And you can see that the upper part of the log shows a straight line. That's where there's no saturation. And then as you hit the water table, you start to see an angled line that it shows an increasing pressure with depth. And that's the ambient hydraulic pressure. So you can pick off where the water table is with some pretty good accuracy. And then on the left-hand side, you see an electrical conductivity log. Electrical conductivity is another way to infer the geology, because low conductivity materials generally have a higher electrical conductivity than higher permeability materials. And you can see that it matches pretty well. You see higher electrical conductivity values where we see high pressures in the HPT log, and then the low electrical conductivity where we see our sand in the HPT log. Another tool that's often used with Geoprobe is called a membrane interface probe. And the membrane interface probe gives you a record of volatile contaminants within the borehole, both in the unsaturated zone and the saturated zone. And the way it works is that there is a membrane on the probe, and volatile chemicals diffuse across this membrane from the soil or groundwater, and they are find themselves in a carrier gas that is circulated back up to the surface. At the surface, it's tested and provides a measure of how much volatile chemicals are in any particular place within the borehole. Some things to remember about this is that the MIP is a qualitative value, so it doesn't give you an exact concentration. It also measures total VOCs and doesn't differentiate say fuel contamination from solvents or anything like that. But what it does do is it can lead you to where the highest concentrations are, and so you can use that to guide where you might want to take samples later. So this is an example of a log where we've done both HPT and MIP. So you get both a record of chemistry and hydraulic conductivity. So you can see that on the left we have again the EC log, which gives us an idea about chemistry, where the permeable zones are. And then similarly, the HPT log, which is the second from the left, gives us an idea of where the permeable zones are. So the low pressure values in the middle indicate a high permeability zone. And then as you get lower in the log, we see high pressures indicating some more low permeability materials. And then the green shaded log here is the MIP log. So that's the organic concentrations. And you can see that the highest MIP readings are just at the bottom of the permeable zone where it starts to get clay. So we've got an area there where you're probably seeing the highest mass flux because you've still got some relatively permeable materials, but you've got the highest MIP concentrations in that zone. Another tool that is used often with the Geoprobe to find free-phase chemicals is called the Optical Image Profiler. And what this tool does is it can detect free-phase hydrocarbons that fluoresce. And what happens is that these free-phase materials, such as gasoline or other fuels, have polynuclear aromatic hydrocarbons, or PAHs, in them. And PAHs, when they're hit with an ultraviolet light, fluoresce back. And that fluorescent light that's reflected back can be measured. And from that, you can determine how much and sometimes even what type of free-phase liquid is there. So the Optical Image Profiler provides a log, and you can see an example here on the right of the fluorescence. And so you can tell in a fairly narrow zone there, that's where you have free-phase hydrocarbons. And that would be the spot where you probably have the highest amount of mass of the contaminants. Some other names for similar technologies to this are laser-induced fluorescence, or LIF, Targos, and UVOS. And that's just industry names from other people's versions of the same technology. So now I'm going to talk about a few case studies where we've used these technologies to gain information and save cost in our investigations. So this is an example of a passive soil gas survey. And so passive soil gas surveys can provide an aerial distribution of contaminants at a relatively low cost because no drilling rig is required. Generally install fairly shallow boreholes with a handheld drill rig and can get a good subset of information to be able to further investigate. One thing is this is, again, used as a screening tool. It doesn't provide any actual concentrations in the soil or groundwater. So the way the passive soil gas works is there's a absorbent cartridge that is inside this canister, and those get put into about a 1-inch hole within the ground, and that cartridge makes the chemicals stick to the absorbent that's on the inside, and then that gets sent to the laboratory, and they measure how much of the chemicals actually stuck to the cartridge. So here's an example of drilling the hole that the cartridge goes into, and you can see that a single person can do that, no drill rig required. Typically they're installed just a couple feet into the subsurface, and they're left there for a couple of weeks. You cement over them temporarily so that they don't have any influence from anything that's going on above the surface. And a 2-person crew can put in as many as 50 of these in a day, depending on how difficult the drilling is with the handheld drill. So in this example here, we are trying to determine what the distribution of TCE in groundwater was. We had a known source on the left-hand side of our map, a known area of impact on the right-hand side of the map. And the question was whether the impacts on the right-hand side were flowing from the left-hand side or whether these were two separate sources. And so what we did to figure this out was we put in 57 passive soil gas samplers. So a number of them on the left side of the street, a line of them down the edge of the street, and then a number of them on the right-hand side of the street. And this was a busy road, so access was difficult. It was not easy to drill within the roadway, and bedrock was very shallow, and so drilling to get actual groundwater concentration was very expensive. You can see from the results here that we have a bullseye of high concentration on the left, and that matches up with what we knew was in the groundwater. We have a bullseye of high concentration on the right, which matches up with what we knew over there. But you can see there's very little in between. So, moving from left to right here, you see the concentrations drop off fairly quickly as you go back towards this other area that we knew had impacts over here. And the line of points along the street showed very little impact. And so that was one of the lines of evidence that we used to show that these were actually two separate sources rather than a single source that it was migrating between. So this is a different example where we're going to use a number of high-resolution site characterization techniques to kind of zone in to answer a problem. So we knew that we had TCE impacts in the upper aquifer at this site, and the groundwater was flowing from the plant building where we knew that there were some sources out to the northeast towards this highway that's up here. The groundwater flow, as you can see, is indicated by the blue arrow, which is a different direction in the conceptual site model here, but you can see the impacted groundwater is down at the base of the upper aquifer. Most of the wells at the site, we saw a nice declining trend in the TCE concentration over time. You can see this one, it went from somewhere near 80,000 parts per billion down to, definitely less than 5,000 parts per billion. Whereas one well, which was out near the edge of the property, kind of bounced around but stayed up at near the original value around 30,000 parts per billion. So the question was, were these impacts at the property boundary coming from under the plant, or could there be a second source? Was it potentially coming from off-site? There's a rail line to the north, and there was some question as to whether that could be a potential source of the TCE that's out near the property boundary. So what we started with was a soil gas survey to try and determine what the aerial distribution of the contaminants were. We had some utilities over in this area that limited the extent of our investigation in that direction, but we did a grid of soil gas points within this yellow box here, and our well of interest is right about where my cursor is on the east side of that box. So we had a 2 to 3 meter spacing, which got denser near our well of interest here. You can see a little clearer on the right-hand picture. But you can see we have a nice distribution of points here to be able to get an idea of what the contamination looks like in this area. The results showed that we have definitely a bullseye, some pretty close to where our high well is here, but separated from the sources that were down near the plant, which is off the page to the lower right here. And that led us to believe that the contaminants weren't traveling from the plant to create that high out near the property boundary. We also see that there's drops off fairly quickly as you move towards the railroad tracks, which are up here on the north side. So we're able to say that the railroad tracks were not likely the source of these impacts out here. So the passive soil gas gave us the aerial distribution of the contaminants near this hotspot, but it doesn't really give us any information about the depth of the impacts. So what we did next was we did some MIP borings to try and figure out where vertically these contaminants exist around this area. So as I mentioned before, the MIP provides us a continuous measurement of volatile impacts within the borehole. Unfortunately, it's not chemical specific, but it does give us a good idea of where the hot zones are vertically. So we did 7 vertical borings across this hot spot to try and figure out where vertically the contaminants were. These green contours indicate where the passive soil gas told us that the contaminants are. And we can see by the red dots here, we did 7 MIP borings across here to try and delineate. And they gave us a distribution that you can see here. And most of the depth of the aquifer, so down to about 36 feet below grade, we didn't see much signal from the MIP borings. You can see it's all fairly low. And then the impacts start right near the interface between the aquifer and the aquitard, which makes some sense with the contaminant that we're dealing with, mainly TCE. So the MIP doesn't provide any actual concentrations. And one thing it also can't do is it can't give you an idea of whether there's actual free-phase contaminants there. So what we did to try and answer some of those questions is we did 4 borings with the Geoprobe to ground truth our data that we got from the MIP and from the soil gas. And so we were able to log the geology and identify where the groundwater is. We sampled both soil and groundwater and did laboratory testing. And then we also collected soil samples to find out if there was free phase present and to evaluate some parameters like fractional organic carbon that would help us determine the rate of transport of the chemicals. So here's a picture of some of the drilling that we did. As I mentioned, we did some testing to try and figure out if we had free phase contamination, and we used a hydrophobic dye called Sudan 4 that separates and gives you a colorimetric indication of whether there's free phase present in any given sample. So here's some of the results parsed out of our borings here. And so you can see that the black indicates what our MIP concentrations were. And then the yellow and orange bars indicate what we saw in our actual soil borings. So the orange indicates where we had our highest PID. And you can see that that is just a little bit into the aquitard, as the yellow indicates where we had the top of our aquitard. So our highest concentrations were just into the aquitard. And then you can see we had one location right at the top of the aquitard where we had a positive test for free phase trichloroethylene. And so that is our highest concentration zone. And then here's some actual lab data that we saw. And this 93,000 is where we saw that positive Sudan 4 test. And you can see the other concentrations match up very well with the contours from the soil gas that we saw. So kind of confirmation that our information is making sense. So from this data, we were able to tell that this hotspot out here was from a separate source and not from transport from the plant building, and also was not from transport from the rail line. And here's a picture of kind of where we ended up with this. So we have some highly impacted groundwater, and then that extends into the aquitard. And what we think is happening is the sources are probably located within the aquitard and slowly feeding into the upper aquifer. But what we found out that these contaminants move very slowly, both because of the permeability of the soil and because of the retardation of the contaminants. So the impacts don't go very far, and we don't have any receptors that are really at risk of becoming exposed to these contaminants. So during the webinar today, we've talked about a number of high-resolution investigation tools that we've been using lately. Multi-level groundwater monitoring systems, some tools that go along with the Geoprobe equipment like HBT and MIP, and also passive soil gas surveys. And what these provide is, at a lower cost, provide us more data to be able to refine our conceptual model and make better decisions about remediation, make better decisions about investigation that still needs to be done. So here, at this point, I'm going to hand it back to Mike Splash.
Thanks, Matt. So we've gone through now 6 of our webinars that help us to understand groundwater contamination. Our next webinar, we'll talk about isotopes and how we can use those to understand groundwater flow and fate and transport of chemicals. So thank you again, and hopefully we'll Have you tune in next time.